This seabird can sleep while remaining airborne above the open ocean. Long flights inspired a question that behavior alone could not answer. Researchers studied breeding female great frigatebirds from a Galapagos colony. A lightweight recorder was attached before each bird returned to flight.
Electrodes measured electrical activity from both brain hemispheres.
An accelerometer recorded head motion and turning forces.
A separate GPS unit tracked position and altitude.
Together, the instruments linked brain state with real flight behavior.
Some recorded journeys covered thousands of kilometers without landing. The longest sleep recordings followed birds aloft for about 10 days. Over deep water, the birds had nowhere safe to perch.
Frigatebirds avoid prolonged contact with the ocean surface.
Their plumage is less waterproof than that of many seabirds.
Getting airborne after becoming soaked would be difficult. Low wing loading makes sustained soaring unusually efficient.
A deeply forked tail provides precise aerial control. Atmospheric updrafts supply altitude without constant flapping. Circling converts rising air into height. Stored altitude then powers long descending glides.
Soaring reduces the muscular cost of staying airborne.
Direct brain recordings finally revealed whether flight contained genuine sleep. Sometimes one hemisphere entered slow-wave sleep, while the other remained more awake.
Bird vision is strongly crossed between eye and opposite hemisphere.
The awake hemisphere could monitor visual information from the open eye. During asymmetric sleep, the open eye often faced the direction of turning. Visual monitoring may help avoid collisions inside crowded rising air. Half-brain sleep preserved some vigilance during flight. Unihemispheric sleep also helps other birds monitor danger on land. In frigatebirds, vigilance appears linked to navigation and nearby traffic.
The hemispheres can differ in sleep depth, rather than switching completely.
Sleep exists along a continuum of hemispheric asymmetry. Frigatebirds also slept with both hemispheres simultaneously. Bihemispheric sleep showed that one awake hemisphere was not always required.
Aerodynamic stability can persist through short bouts of whole brain sleep.
Updrafts reduce the need for active altitude control.
Most flight sleep occurred while birds circled in rising air.
Light provides time before a sleeping bird approaches the water.
Birds generally remained awake near the ocean surface.
Foraging demands favored wakefulness during daylight. During flight, that half-brain sleep allowed rest without surrendering all visual attention. Eye state matched the turning direction during many asymmetric sleep bouts. Either hemisphere could become the deeper sleeping side. Sleep arrived in short fragments rather than long, continuous periods. Typical flight sleep bouts lasted only around 12 seconds. The longest uninterrupted episode remained under 6 minutes. Dozens of brief naps accumulated across darkness. Sleep occupied only a small fraction of time aloft.
Recorded birds slept during less than 3% of flight.
Daily flight sleep averaged less than 1 hour.
Ecological demands kept the birds awake most of each day and night.
Frigatebirds track ocean features associated with future feeding opportunities.
Following changing ocean patterns may require sustained attention. Large predators can push prey toward the surface. Frigatebirds capture food while remaining airborne.
They sometimes harass other seabirds for food.
Kleptoparasitism provides another aerial feeding strategy.
Efficient feeding must support days of continuous movement. Aerodynamics minimize the cost of remaining aloft. Night flight involved even less flapping than daytime travel.
Despite sleeping in flight, the birds obtained remarkably little sleep.
Land sleep exceeded flight sleep by more than an order of magnitude. Back at the colony, sleep became longer and deeper. Land allowed more continuous slow-wave sleep.
Flight sleep was generally lighter than land sleep.
A secure surface removed the need for aerodynamic control.
The recorded females were returning to chicks between foraging trips.
Parental demand made long foraging journeys necessary.
Food resources could lie thousands of kilometers away.
Returning to land created an opportunity for extended sleep.
Researchers still debate how completely land sleep repays losses from flight. Available recordings do not capture every transition between sea and land. Longer studies could measure cumulative sleep recovery.
New biologgers may reveal how sleep changes during longer flights.
Tracking studies show longer airborne journeys than current brain recordings cover.
Continuous flight does not automatically prove continuous in-flight sleep.
Brain activity is required to identify sleep reliably. EEG distinguishes the major avian brain states.
Rare flight bouts included rapid eye movement sleep.
Brief REM did not visibly disrupt the recorded trajectory.
Avian REM episodes can last only seconds. Reduced muscle tone was brief enough for flight to continue. Atmospheric support may buffer momentary reductions in active control. Several safeguards overlap during these rare episodes.
REM sleep ended rapidly. Most sleep aloft consisted of slow-wave sleep. Both asymmetric and symmetric patterns occurred.
Sleep strongly favored circling flight.
Tension remained highest near potential feeding zones.
Birds often gained height before sleeping.
Flight sleep combined several strategies rather than one simple autopilot. Altitude reduced immediate danger from descent.
Thermals supplied passive support.
Unihemispheric sleep preserved directional awareness. Brief naps limited exposure to reduced attention.
Together, these features made sleep aloft possible.
Human responses cannot be inferred directly from a seabird.
How frigatebirds function on so little sleep remains unresolved.
Several physiological explanations are still under investigation.
Sleep may be regulated more locally than whole brain labels suggest.
On land, the bird finally gains a stable place to rest. Both hemispheres can enter deeper sleep. Daily sleep rises to more than 12 hours. Slow wave activity becomes stronger. Adhika.
Sleep episodes become more continuous. REM sleep also occurs safely on land.
Resting conditions permit fuller sleep architecture.
Land sleep likely contributes to recovery. Complete repayment of lost sleep remains uncertain. Future studies may reveal the hidden costs of oceanic sleeplessness. Other species may use different sleep strategies. Long flight alone cannot establish sleep on the wing.
Smaller instruments could expand direct tests.
New recordings may reveal multiple solutions to sleep during migration. Great frigatebirds remain the first birds directly proven to sleep in flight. Their recordings revealed several unexpected sleep states.
One eye can monitor the turn while the opposite hemisphere rests.
Sometimes the entire brain sleeps while flight continues.
Yet total sleep remains astonishingly small at sea. Frigatebirds sleep in the sky by combining brief naps, soaring, and partial vigilance.